Hello, and in this video we will be looking at waves and particle nature of light, specifically for EDEXCEL. We will look at specification points 61 and 62 in this video. Specification point 61 states that we need to be able to describe longitudinal waves in terms of pressure variation and displacement of molecules. And specification point 62 states that we need to be able to describe transverse waves. Well, what are longitudinal waves? And are there any examples? Sound is an example of a longitudinal wave, with the direction of wave displacement being the same as the direction of wave propagation. More examples can include seismic P waves. So as we see the following diagram on the left hand side, the direction of wave propagation, which is more commonly known as the direction of wave travel, is going from left to right, and the direction of wave displacement is the same as the direction of wave propagation, which also goes from left to right. So to summarize this, the direction of wave displacement is parallel to the direction of wave propagation, and examples of longitudinal waves can include seismic P waves and sound. Now we need to understand, well, what happens to longitudinal waves which travel through mediums? Longitudinal waves, such as sound, travel in a series of compressions and rarefactions. At points of compression, the molecules of the medium are close together, which results in a pressure increase. At points of rarefaction, the molecules are further apart, resulting in a pressure decrease. Now, looking at the following diagram on the right hand side, we can see that the direction of travel of molecules is from left to right, and we can see at points of compression the molecules are packed tightly together, therefore there's a higher pressure and lower velocity for the molecules, and at points of rarefaction they're more distributed, so therefore they would have a lower pressure and high velocity. So to summarize this, sound is a longitudinal wave. Longitudinal waves have direction of displacement being the same as the direction of wave propagation. They travel in a series of compressions and rarefactions, and molecules are closer together at points of compression, therefore pressure would increase, and molecules are further apart at points of rarefaction, so therefore pressure would decrease. Moving on, we now need to have a look at transverse waves. Well, what are transverse waves, and more importantly, are there any examples? A transverse wave is a wave in which the direction of wave displacement is perpendicular to the direction of wave propagation, and examples can include light waves, radio waves, and water waves. The following image above is basically a picture of a sine wave. So as we can see, the sine wave propagates from left to right, and the direction of wave displacement is perpendicular to the direction of wave propagation, which is why we have these peaks and these drops at certain points along the graph. So to summarize this, the direction of wave displacement is perpendicular to the direction of wave propagation for transverse waves, and examples of transverse waves include light, radio, and water waves. Thank you all for watching. I hope this video has cleared up any questions anyone's had about transverse waves and longitudinal waves. Thank you and goodbye.